What is the basic concept of algorithm?
Algorithms are step-by-step set of instructions or procedures for solving a specific problem or programming a task. They are a fundamental concept in computer science and mathematics and are used in various fields. The basic idea behind algorithm is to define a clear and unambiguous sequence of actions that, when followed, will lead to a desired outcome. Algorithm provide a way to automatic process, make decisions, and manipulate data efficiently and accurately. They are essential for taking ranking from sorting a list of numbers to searching the internet, and they serve as the fundamental for computer program and software development. In essence, algorithms are the building blocks of computational problem solving.
What is the theory of algorithm complexity?
The theory of algorithm complexity, also known as computational complexity theory, is a field of computer science and mathematics that focuses on understanding and analyzing of the efficiency and requirements of algorithms. It seeks to quantify how the time and space needed to solve computational problems grow and the size of the input increase. The theory categorizes algorithms into different complexity classes, such as concept time, linear time, quantitative time, and more, using big O notation to describe the performance. It also addresses fundamental questions like the P versus NP problem, which explores the flexibility of efficiently solving complex problems and NP complexity, with identify particularly challenging problems. Overall, algorithm complexity theory helps us assess and compare the efficiency of different algorithms and understand the limitations.
What is the type of asymptotic time complexity?
Asymptotic time complexity refers to how the running time of an algorithm grows as the size of the input approaches infinity. It is a way of characterizing the efficiency of an algorithm without getting into specific details. There are several common types of asymptotic complexity. Constant time. The algorithm running times remain constant regardless of the input size. This is the most efficient type of complexity. Linear time. The running time increases linearly with the size of the input. If the input size doubles, the running time approximately doubles. Logarithmic time. The running time grows logarithmically with the input size of the input increases. The running time increases but at a slower rate than linear time. Linearitmic time. This complexity is common in efficiency sorting algorithms. like Marcus sort and quick sort. The running time between linear and quadratic. Quadratic time. The running time is proportional to the square of the input size in considerably less efficient than linear or logarithmic time. Cubic time. The running time is proportional to the cubic of the input size, making it less efficient than coordinate time. Exponential time. The running time grows exponentially with the input size, which can become extremely slow for later inputs. Factorial time. The running time is factorial with an ever slower than exponential time and is often impractical for later inputs. These notations include Big O notation. Provide a way to compare the efficiency of algorithm and understand how the performance scales with input size. Algorithms with lower order complexity are generally more efficient and provide for longer datasets.
What is the type of algorithm based on Big O notation?
Big O notation is a way to categorize algorithms based on their asymptotic time complexity, which describes how the running time of an algorithm grows concerning the size of the input. Here are some common types of algorithms based on Big O notation. Constant time algorithms. These algorithms have a constant running time that depends on the input size. Assessing an element in an array by its index is an example of O1 operation. Logarithm time algorithm. Algorithm with logarithm time complexity grows slower as the input size increases. Binary search is a classic example of an O log n algorithm. Linear time algorithm. The running time of this algorithm increases linearly with the input size. For example, iterating through an array to find a specific element has O(n) complexity. Linear time algorithm. Algorithm is the category are more efficient than quadratic but slower than linear ones. Many efficient sorting algorithms like Marcus sort and quick sort fall into the category. Quadratic time algorithm. Algorithms with quadratic time complexity have running time proportional to the square of the input size. Nested loops often relate to O and 2 algorithm. Polynomial algorithm. The algorithm have running time that depend on the input size raised to some constant power k. For example, bubble sort has O and 2 time complexity. Exponential time algorithm. These algorithms grow very quickly with input size and can become impractical for even moderately sized inputs. They are often associated with exacerbate search problems. Factorial time algorithm. The algorithm have running time that increases at an alarming rate, rendering them inefficient for larger inputs. They are common in combinatorial problems where all possible combinations must be considered. Understanding an algorithm time complexity in terms of big O notation helps is chosen the most efficient algorithm for a specific problem, especially when dealing with longer data. Lower order complexity are generally more desirable for efficiency.